let's move on to the next talk. So the next talk will be given by Professor Jinxing Ma, my colleague. So I will introduce him. Professor Jinxing Ma currently works at Guangdong University of Technology. He got his PhD degree from Tongji University. Prior to joining Guangdong University of Technology, Jinxing had worked for 5 years at UNSW Sydney, during which he conducted continued research on electrochemical processes for desalination and oxidation of refractory organics. Jinxing has published over 100 peer-reviewed papers, and he has been recently awarded as one of the Australia's top 40 young researchers. And let's welcome him. Jinxing, now the stage is yours.
Okay, second. Sorry. Hi, good morning, everyone. So this is Jinxing Ma from Guangdong University of Technology. So many thanks for the kind introduction from Professor Wang. I assume that why my presentation just follows Professor Wang's. The reason is that because I sit next to his office. Just now, Professor Wang discussed about the salt party.
Sorry to interrupt, Jinxing Ma. We can't see your slides. Please try to switch your screen.
Okay. Okay, let me try that one again. Sorry.
No problem.
Okay, see
Yes,
this
we
one
can see it
again?
now. Could you go to full screen?
Okay.
Perfect. Go ahead. Thank you.
Okay. Yeah, that's right. So just now, Professor Wang discussed about the salt part in brine management. So I will discuss something else. So it's about organics removal in the brine concentrate. So the topic of my presentation is characterization and the decontamination of the membrane concentrates from the coal chemical industry. So this presentation is on behalf of Mr. Xiang Tongkou, one of my PhD students, and my collaborators, Dr. Shika Gak and Professor David Waite. So first of all, I'd like to introduce the background. So while China and the United States recently achieved agreement in response to climate change, and China has promised its best to control carbon emission, coal is still dominate primary fossil resource in China now and contribute to around 60% of the domestic energy consumption. Also, this accounts for half of the global use. More importantly, coal is an important resource in the chemical industry. So around 30% of the global production of methanol and ammonia comes from China's coal chemical industry. Meanwhile, coal chemical industry also leading wastewater discharge. For example, the wastewater comes from the coal gasification process, also has a very high concentration of COD in addition to the high salinity. And many of the complicated compounds are refractory. In addition to the traditional biological treatment process and the physical chemical processes, membrane technology has been recently used to polish the effluent to meet more restricted standards, such as the just now Professor Wang mentioned about the zero liquid discharge scheme or the so-called minimum liquid discharge scheme. During the concentration of the brine stream, so the trace organic matters also be accumulated in the pipeline. So what we do with the brine, so before the evaporation or the crystallization processes, we also need to remove part of the organics to maintain the stability of the process. So in this process, we have two major challenges. The first one is how to characterize the complicated water matrix because it contains various organic pollutants. Most of the current technologies are low throughput. The other one is to develop a viable decontamination technologies. So we need those technologies has low cost, high oxidation capacity, and the low sludge yield, because the waste also being controlled in the ZLD process. So in response to those challenges, we have this research work starts with the collaboration with CCI, China Co-Research Institute. So it has a scheme to find a co-chemical wastewater treatment technology. First, we collect a number of wastewater samples from 4 co-chemical wastewater treatment plants. The first one, the plant 1, treat a combination of, actually it's a separated wastewater. One stream comes from processed wastewater, the other one is from saline wastewater. So after treatment, we collect those from the RO concentrate. The second plant treat about a combined wastewater, and the water sample comes from the concentrate from the second stage RO system. The third plant also is a little bit different from those two, because actually it's a plant to treat the co-chemical industry wastewater. Actually, it is a kind of concentrate. Then after the pre-treated of the effluent from the concentrate from the high pressure RO system, we collect the permit from the rejected fraction from the UF system. The last one is a plant treating coking wastewater, and the water sample comes from the RO and the EB process. So the first table describes the chemical composition of the CCI concentrate samples. For the concentrate from plant 1, it's a co-gasification wastewater. We found a pretty high hardness and also high chloride concentration. Because during at this pH range, the chloride the chloride can scavenge hydroxide radicals. So this poses a challenge to select an effective AOP process. So for the concentrate from plant 2, it's also a co-gasification with water. So since nanofiltration is implemented prior to the RO unit, so we didn't find pretty high. We didn't find high hardness concentration, but we found high ammonia concentration and bicarbonate ions concentration. So the problem for ammonia is that if you choose ozonation process, ammonia may react with ozone. For bicarbonate, it is also a scavenger for hydroxide radicals. For the third plant, M1, because it's treated water from RO concentrate, so the COD concentration in this stream is not that high, so we didn't do any further detailed work on this stream. Okay, so the last one is a concentrate from plant 2. From plant 4. So it's a coking with water treatment plant. So it also has a high concentration in hardness ions and chloride concentrations. And it is surprising to it was surprising to find that the fluoride concentration in all of these wastewater exceeds the discharge limit. But because this is beyond the research goal of this project, we didn't do much work on the fluoride removal. First, we use LC mass to analyze the organic composition of the wastewater. And we found there's a dozen of chemical volatile compounds has the mass to charge values between 50 to 1,000. So it means if we only choose 1 or 2 target compounds to investigate, so this may not be representative for this kind of wastewater because it's too complicated. So what could be a good solution? So since we have a long time experience in using LC-OCD technology, so it's a kind of a combination of conventional LC with organic carbon detector to divide the organic compounds into different groups. So actually divide the organics into biopolymers, humic substance, building blocks, low molecular weight acid, and neutrals, and hydrophobic compounds. So we wonder whether it's a good technology or bad technology for the characterization of coal chemical industry concentrate. So for all the wastewater samples we collected from the concentrate, the RO concentrate, we found the samples from the first 3 units has a high low molecular weight neutral concentration, followed by humics and biopolymers. For the last one, the coking wastewater treatment plant, the concentrate from the coking wastewater treatment plant, we found the humic substance is most dominant fraction, followed by hydrophobic organics, building blocks, and the low molecular weight neutrals. So probably we have an answer to the first challenge, how to characterize the complicated organic compounds. So the second question is what technology we may choose for the process treatment, for the treatment process. So we have compared a number of LP processes, including Fenton and others, and finally we choose to use ozonation or catalytic ozonation because it can directly oxidize organics by molecular ozone or via ozone decay that generate hydroxide radicals. So first one, according to the LC-OCD results, about 76% of DOC could be resistant to ozone attack, with the rate constant only being 0.02 per minute. Likewise, the humic substance in the DOC are also ozone resistant, and they have demonstrated a similar rate constant of 0.03 per minute. During the oxidation of the reactive part, it generates humic substance. However, the original low molecular weight neutrals are not ozone reactive, and the commercial rate constant only is 1 order of magnitude lower. In existing studies, fluorescence methods has been widely used as a good indicator to evaluate whether the oxidation process is effective or not. So we compared those two technologies. One is the widely used EEM, and the other one is the LC-OCD we proposed in this study. We find most formic acid-like and humic-like substance in the concentrate are likely ozone reactive. It means they have a good removal rate. But these two parts only contribute a very small amount of the humic-like substance in the membrane concentrate. So if people report that their process has a very good kind of performance for the concentrate removal based on the fluorescence signal, so we may have a question mark here. So is it very representative of the membrane concentrate? So our task is how can we improve the performance, because we only remove like 30% of the DOC from the membrane concentrate. First one, we try to dose peroxide into the ozonation process to induce the peroxing process. However, addition of 10 to 100 micromolar peroxide at any time to initiate the peroxing process insignificantly influence the organic removal, probably due to the nature of the refractory organics. As compared to the organics, the peroxide is more reactive with hydroxide radical generated in the system. So the excessive peroxide actually damages the hydroxide radicals. So is there any other solution? So in this case, we choose catalytic ozonation. As can be seen from this figure, so according to the catalyst we prepared, so the removal efficiency can be improved from like 30% to 80%. And the mechanism is ascribed to the selective absorption of the refractory compounds onto the active sites as compared to the abundant ionides, that is chloride. Also, the absorbed ozone on the surface could be involved in the direct electron transfer with the absorbed organics, or the hydroxyl radicals could be generated in the system to facilitate the conversion or degradation of the refractory organics. The conclusion, therefore, this is the conclusion of our study. The first one, we found LC-OCD technology could be a reliable technology to characterize the composition of the refractory organics in the concentrate. And we found humic substance and the low molecular weight neutrals are the dominant species in all CCI concentrates. While the matrix effects, that is the high salinity, we found played an insignificant role in the oxidation process. The low reactivity of the DOC was ascribed to the refractory property of the humic substances as compared to their other species in other matrices, for example, the humic acid in fresh waters. So finally, we suggest to use ALP processes that can capable of generating stronger oxidants, such as hydroxyl radicals from catalytic ozonation or from anodic oxidation for the concentrate management. Thank you for your listening. So I would like, any questions will be appreciated. Thank you.
Thanks, Professor Ma, for the very nice talk. Any questions from the audience? Okay, so may I ask a question, Jinxing?
Sure.
Yeah, so you mentioned at the last of your presentation that you apply a catalyst in the system to remove the pollutants or contaminants. So how do you apply the catalyst? You use you add some powders of the catalyst in the system, or you immobilize the catalyst on a plate or something?
Yeah, man, thanks for the nice question from Professor Wang. So actually, it's like a pellet catalyst. So we have a carrier. So the carrier is aluminum oxide. So we load the active components onto the surface of the catalyst. So actually, we compare a number of metal oxide, and they have different properties and different mechanisms for oxidation of different compounds. So we then fill the pellets in a column. So the ozone is provided from at the bottom of the column. So it's a flow-through configuration for continuous operation. Yeah.
Okay, thank you.
Many thanks.
So if there's no other questions, maybe we can move to the next speaker.
Professor Wang, I have one question.
Sure, Dr. Xiang.
Chat box.
Please.
So my first question is about, since ALP is a high-cost solution, so I want to ask Professor Ma, so what technology would you recommend that can be combined with ALP together to reach a cost-effective solution?
Yeah, so I will answer the first question. Many thanks for the question from Dr. Xia. So actually, we compare a number of ALP process that can be used for the brine management in this scenario. Currently, Fenton is also being widely used in the concentrate management because it has low cost. But the problem is that it generates a large amount of the chemical sludge. So now some of the industry zone, they do not have the control of the solid waste. So that's fine. They use the Fenton process. But for the future, because the treatment price for the chemical sludge is over 1,000, at least 1,000 RMB per ton. So it cannot be further optimized to achieve this goal. So that's why we finally suggest to use the ozonation or catalytic ozonation process, because it do not generate any chemical sludge. So we also has done any. We also have done a economic analysis of the process, and we found the big issue for the catalytic ozonation is the cost of the catalyst and its regeneration cost. So currently the cost for the catalyst now is around like 30 to 50,000 RMB per ton. So it's or per cubic. So it's a cubic meter. So it's a big issue. But the ozone itself is not expensive. So, for example, per ton, for any per ton of wastewater treated, so the operating cost is only like 0.2 or 0.1 RMB per ton. Yeah.
Okay, thanks a lot for your answer. Yeah. Another question is about I found you have a strong tool called LCOCND, so you can do the fingerprint analysis for the complex water chemistry. So for the you mentioned the coal gasification process, and the coal to chemical is has multiple steps. So I wondered whether you have found some common trends or in water chemistry for coal to chemical water.
So we finally actually we use some target compounds. So it may have similar reaction rate with those compounds in the wastewater, but you cannot find one they have the same chemical structure. So you only have one like representative for one group of the chemicals. So because actually so they are very complicated.
Okay, thank you.
Yeah, many thanks for your question.
Okay, I think that's all for Jinxing's talk, and we'll move to the next presentation, and I will let Dr. Xia to introduce the speaker.
Dr. Xia and Dr. Wang, and I would like to announce that the third speaker didn't show today. I just want to ask you too, how are we going to proceed? Do we go to the next speaker, 05C04, or we wait for a few minutes?
Maybe we will go to Shan's presentation.
Yeah,
it's also fine. Yeah. Okay, thank you. I will leave the